Last time we have discussed in detail the different approaches seen for the one-dimensional equation, which was actually ordinary differential equation, but all the main steps which are then also quite similar for 2D and 3D, we have discussed with this one-dimensional simple Poisson equation. Now let's look at 2D and 3D, and for this sense we have prepared here the following equation, which is a Poisson equation in this sense. So I just try to get it. So we have, as you can see here, this part that minus the divergence, then we have a material parameter. I just enclose it here, new, and for me important is that you see this material parameter also depends on the space. Gradient u is equal to 0, so u is our physical quantity. U could be, for example, the scalar electric potential, and nu could be the permittivity. And in order to get a unique solution, we have fully defined on the boundary, on one part of the boundary, which we will call the essential boundary, gamma E, E for essential. We have a Dirichlet boundary condition, so we know the physical quantity there exactly. And on the other boundary, which is the natural boundary, or as seen from the mathematical point of view, the Neumann boundary condition, the flux, so the gradient of a scalar potential scaled with a material parameter in normal direction is called the flux. So the flux is prescribed on this part there. Okay, so in this sense, then we we then have the following. As you know, our first step is to introduce a test function, and for this test function we call it v. So v is our test function here. We multiply the partial differential equation by this test function, and we integrate over the whole computational domain. Yeah? And as you can see here, nothing else has been changed. So it is, in this sense, the multiplication with a scalar test function, our scalar partial differential equation, and we integrate over the whole computational domain. So now, when we do the following, we call new gradient u as a vector f. Yes, and you know that we have the following identity, that the divergence of a scalar multiplied by a vector is shown here. This is this part here, vector f multiplied with the test function v, which is scalar quantity. According to the product rule, we can rewrite this as follows. It is the gradient of v, scalar product with our vector f, plus v divergence f. Okay, so in this sense, we now can use this and substitute it in our integral we had previously, where we had exactly this term in the integral. Perhaps you remember, I just will mark it. We had this term in the integral. And so this term can be substituted by the divergence of the product minus the gradient of v dot product with the vector f. And that is exactly what we have. Due to this minus, we put it here. We get here this part, which means we have now just a first order partial derivative on the unknown u. We have a dot product with the gradient of the test function. Now the gradient also, also the test function now has a spatial derivative. But what is most important is that, as you can see here, now our material parameter, which could even have a jump between interfaces, now on this material parameter we have no spatial derivative. So that is a really huge gain we obtain due to this reformulation by the divergence theorem we have applied, or simply speaking by integration of parts. Yeah, and in addition, we should not forget we have also this second volume integral where we have the divergence of this part here. So the test function with our material parameter gradient of the unknown. Yeah, and that we clearly know that on this term here we can apply our Gauss integral theorem, which means that we convert this here to a surface integral. So in total, as we have started, that was our starting part. Just have to get the pen. I don't get the pen. Okay. Perhaps it's easier to take it with this one. So we see it exactly here. We just have to get our tools again. Yeah, so that is important. So that was our starting term, and that we convert exactly without any approximation into a volume integral. We can see here where we have, as I have told you, just a first order derivative on our unknown u, also a first order derivative via the gradient on the test function, and the material parameter free here without any spatial derivative. And in addition, we have a closed surface integral, and we know we have prescribed boundary conditions on this surface, which means that we can substitute it now in this sense that this surface integral we divide in the integral over the essential boundary and over the Neumann boundary. Now, what we know is that at the essential boundary we already know our physical quantity u because it is prescribed by some value or 0, but we know it. So we will also choose a test function which is 0 on this gamma e, the essential boundary. So this term will always cancel out. Yeah, and here we have no problem to put in the prescribed flux as we have seen before, which means that the first part is that we set the test function to 0 at the Dirichlet boundary because we already know the physical quantity there, and we insert the inhomogeneous Neumann boundary condition, so we get this prescribed flux term Qn. And that is also why we call this boundary, which you call this boundary condition, you call a Neumann boundary condition in classical mathematics. In the context of finite element method, you call it a natural boundary condition because you directly incorporate it in the weak formulation. So the weak formulation is now as follows. We search for the unknown u. We already know the unknown u on a part of the boundary, which is the essential boundary, and it has to fulfill this equation here, where we have the gradient of the test function dot product with the gradient of the unknown u integrated over the computational domain, and that is equal to a right-hand side, and the right-hand side in this sense is a computation along the natural boundary where we multiply the test function with the prescribed flux on this boundary. And that has to be fulfilled for all test functions in this sense. So that is the main part what we have gained. What I have neglected here, a mistake on the slides, sorry, our new, which is a material parameter, should stand here on this part. Okay, you cannot see it, so I have to switch on the commands. So here actually we should have our new parameter in here. Yeah, I have forgotten here our material parameter to put it in. Okay, so now clearly for most cases we are also not able to solve the weak formulation analytically. And that is why we do a space discretization, meaning from the computational domain, we subdivide it in small triangles or quadrilaterals in 2D, or tetrahedra or hexahedra, pyramids, wedge elements in 3D. And we introduce basis functions. Basis functions stand for the unknown as well as for the test function. And as we have discussed already in the 1D case, that also turns over for 2D and 3D case. The property we need for our test function is the so-called local support, which means in this sense that we have this property here, that when we evaluate such a such a basis function at any position, then it is equal if we evaluate it exactly at the position. So you see here, for example, any shape or basis function NA, which is exactly 1 for the node A and for all neighboring nodes, which is this node here, and which is this node here, and which is this node, it goes to 0. So it is exactly 0 at all the other nodes. Okay, so now after space discretization, we can here go on and do here the approximation of our test function and of the physical quantity. And this is, as you can see here, exactly the same as we have done it for the 1D case, that now the discrete test function and the discrete unknown, that is discrete because we have here this h is always the symbol that something has been discretized, is equal to a sum of the basis functions multiplied by coefficients. And actually we are really interested in the coefficients of the unknown u, which are these so-called ub. Yeah? We are not really interested in VA because it's the test function. We want to get the solution at all our finite element nodes we have here in our discretization, where we don't know our physical quantity u. We want to get these coefficients of such ansatz. And you can do this ansatz with the sum because we have this very important property, the so-called local support. And therefore, what we also get out when we evaluate UH at a position, for example, at this node, then we exactly get out U at this node. And therefore, we can do this kind of answer. So exactly the same, just that our basis functions are now a basis function of x and y, or x, y, z in 3D. Okay, so we use now and take our continuous weak form and we substitute in this weak form now this approximation we just have discussed. So that is exactly what is standing along this line here. And what you see is clearly the following, and that we should elaborate, is that the coefficients VA are constants and also UB are constants. Yeah? So when we apply the nabla operator, then this is 0. So the nabla operator actually just can operate on the basis function and get something different from 0. The other are constants, which means we can even put it out of the integral. But first we take the sum, and we take the sum in front of the integral, and also this sum we can put in front of the integral. And that is exactly what we have then in this next line, which is as follows. As you can see here, it is that we have here put out the coefficients of our ansatz for the test function, and I'm missing the coefficients. Okay, there are really some mistakes we have made, so we should put it on there. I will try to write it clearly. What is missing here is, I have to take it with the pen. Clearly, what we also should put in here is exactly our unknown u. Okay, it's catastrophic to write on it ua. So that should be a. Okay. And now you can see in this sense that we can, for example, for the first node, we have then V1. We can set this to 1, divide it, and then we have one equation, because the sum is going also for b equal 1 to the number of equation, not number of nodes, because we just count those nodes where u is unknown. And that means we can collect everything, and what we get is then such a system of equation that ku is equal to f. U is now an algebraic vector containing all unknowns. F is the right-hand side vector. As we know, it is due to the inhomogeneous Neumann boundary condition, and K is our system matrix. Now let's have a closer look to it, how they are computed, and that is shown here. You see all the entries, what we have is as follows, that we have here these entries KAB, and this KAB is simply computed by this equation here. We have to take the gradient of the basis function at the corresponding equation A, dot product with the gradient of the basis function at the equation B. That is why we have AB here. We should not forget our material parameter and integrate over the whole computational domain. Even simpler, it is for the right-hand side. Each entry at the right-hand side is as shown here. We have to integrate over the boundary, the Neumann boundary, where we have a prescribed flux, and scale it with the basis function NA. And that we have to do for all nodes, for example, let's say this node, and so on, all the nodes where we have a flux Q n different from 0 and belonging to the Neumann boundary. Okay, clearly what we immediately see is the following. Why do we integrate over the whole computational domain when, for example, NA has this local support? So it will just have an overlap with NBs, where B could be this node, or this node. For all the other nodes, there will be no overlap between the two basis functions. We also have seen this very nicely in 1D. In 1D, you just can have a left and a right neighbor basis function where you have an overlap. Here it is in 2D and even a little bit more complex in 3D. But what we see that for a large part of the computational domain, we will have no contribution because there is no overlap between the basis function NA and NB. So there should be a possibility to compute this more efficiently. And that is what we go on the next slide. And as you can see here, we could now subdivide our integral in this sense that we take here a sum over all our finite elements. So NE is the number of finite elements, and we just integrate over each element domain. Is the same as we integrate over the whole computational domain. We have subdivided the computational domain omega in individual omega e's, where E is the corresponding element we have obtained due to the discretization. So in this sense, what we actually then have to do is we will compute this here, and this part what we have here will be called in this sense a element matrix. Therefore I call it a small k with index E, and this is a so-called assembly operator. Yeah? So we will compute these entries and then we'll assemble it to the system matrix. And how we do it, we will see in a few minutes. Okay, and the entries K, P, Q of each of these element matrices is very simple computed. We now just integrate over the element domain of the element and use the basis function which are defined there for each node. Let's say we have a quadrilateral, then we have 4 nodes, for example, a bilinear quadrilateral, and then we get here, in this sense, element matrix with 4 times 4 entries. Okay, so still what is not really practicable for implementation clearly is the following, that each element can have a different shape. Yeah, we have seen when you do and generate your computational grid, each element can have a different shape, different triangle, different quadrilateral. To evaluate the integral, yeah, as we have it here, will not be as easy over such a shaped element. And the question is how to define the basis function, the NP and NQ with global coordinates, yeah, because we still have this computational grid. And that brings us now to the idea of a so-called reference element. A reference element, as you can see here, is the following. This is here our reference element. We call it also the so-called unit space. For a quadrilateral, it is a nice element going in xi direction from -1 to +1 and in eta direction from -1 to +1 with 90-degree angles. And that means we have to find a mapping from any quadrilateral to such a reference element. And that we can do simply by the mapping concept as shown here, that we express the global coordinate x and y as it is also shown here. Yeah, we have here the coordinate axis x and y, that each node x and y is expressed by xi and eta. We call xi and eta the so-called local coordinates, as we see here in the unit space. It's going from +1 to -1 in this unit space. Yeah, and we can also write it as a sum in this case, where xi and yi are the global coordinates of the 4 nodes, 1, 2, 3, 4, the x coordinate and the y coordinate. And we have here so-called basis functions ni, which are functions of the local coordinates xi and eta. Yeah, and we can do this mapping because we know the 4 coordinates. We have here the first node in the unit space, which has the coordinates 1, 1. We have the second node, which has the coordinate -1, 1. The third, -1, -1. And the fourth coordinate 1, -1. Yeah, and then it is just a question how you define in this sense the basis function. Yeah, in this case we do the geometric mapping, and for this case I just go to one node because it's easier to write there something. So we have the basis functions Ni, which are functions of psi and eta. Yeah, and you can now do the following, that you say you define this in the following sense as a bilinear function. Yeah, so this is equal to sum alpha 0 plus alpha 1 psi plus alpha 2 eta plus alpha 3 psi eta. Yeah, and we know the I is going from 1 to 4, and for this we have the coordinates psi I and eta I. And that means we have here 4 unknowns. So we have this alpha 0, alpha 1, alpha 2, alpha 3. But we also get 4 equations because the I is going from 1 to 4. We have the 4 nodes in our reference element, and this means by this case that we get here this mapping between the reference element and the physical element, the physical space defined by x and y, the unit space defined by psi and eta. Yeah, and so we have here 4 equations for the x coordinate, where x takes on the value of the x coordinate of the first node, of the second, third, and fourth node. And we also will have just the same ansatz for the y coordinate, and that will also give us 4 equations. When you do this, you will end up and you combine it in this very nice form of these functions, as you can see here. So we have here this function Ni as a function of psi and eta. And as you can see here, it is a product of 1 plus psi I psi multiplied with 1 plus eta I eta. And I have just drawn down here the basis function N1, which is the basis function to this node here, N2, which is the basis function to this node, N3, which is the basis function to the node back, and to this node we have N4. Okay, so these are actual now interpolation, sometimes called functions or shape functions. We can also call them basis functions in this sense when we also use these functions for approximating our physical quantity, which was in our case the u. And in this way, when you choose the same shape, as you can see here, you have to take, we call it here shape function. Sometimes you will find it in books interpolation function. I like basis function. When these are the same for the mapping as well as for the physical quantity, then we call this the so-called isoparametric element. And that were the standard elements at the beginning of the finite element method, and still in a lot of commercial programs are there also the standard approach. However, as you see here, what I have written is this important note here, that this is not the optimal concept. Why is clear? Because we have the freedom to choose different functions from the mapping between the physical element and the reference element, and we can have different functions for approximating our quantity. So with this isoparametric approach, we lose more or less one option because we take the same basis function. Have here for the mapping basis function which are bilinear or even quadratic or cubic. If you have a geometry which is very complex, where you have curved boundaries, then you clearly want to have a good approximation with this mapping between curved elements and a reference element. On the other hand, if you solve there a very a partial differential equation with a very smooth function, why do you use higher order basis function? You could use linear elements and you even get very good results. So in this sense, it could be also vice versa. You have a very simple domain, but you want to compute it very efficiently. Then you can have a very coarse grid. You use very simple basis functions for the mapping, but you use higher order, cubic order, for example, for approximating the unknown quantity. So in this sense, it is a choice, of course, but not the optimal choice, because we lose a freedom in this sense how we do the mapping and how we do and approximate our physical quantity. Okay, still a lot of things have to be done so that we can really go further for a computer implementation. And in this sense, what we will now introduce is the following, that we already have this mapping concept, and due to this mapping concept, we also have to do a transformation of our differential operator, which means that the nabla operator with respect to psi can be expressed by the nabla operator with respect to x by the so-called Jacobian matrix. And the Jacobian matrix is nothing else as the partial derivatives of the global coordinates with respect to the local coordinates. And as you also know, when you do a substitution, then you also have and get the volume increment for the volume integral for the global coordinates can be expressed by those of the local coordinates, but we have to scale with the determinant of this Jacobian matrix. And so you see, when you multiply now, I should take the pen, when you multiply now this equation here, I'm speaking, with the Jacobian inverse, then you can express the nabla operator with respect to the global coordinates. That is what we actually have within our formulation by the nabla operator with respect to the local coordinates. And that's important because we have basis functions which are now basis functions as a function of the local coordinates psi, eta, and in 3D you will have also zeta. So this brings us to the fact that when we use this relation, then we can rewrite our integral here, where we have the nabla operator with respect to the global coordinates on the basis functions, which are functions of the local coordinates, by really the nabla operator we have here, by the nabla operator here, which we can compute, because it's the nabla operator with respect to our local coordinates in 2D psi and eta. We have the basis function being expressed by the local coordinates psi and eta, so we can compute it. Yeah? But clearly what comes up is the Jacobian matrix, but this Jacobian matrix can be computed, and we will see it explicitly in a few minutes. The same we have to do for the second term, here the second term, and that's why the inverse of the Jacobian is also popping up here, and we have here the gradient with respect to the local coordinates psi and eta in 2D, and don't forget here that we also need the determinant of the Jacobian matrix. Okay, so in this sense, we have now the following, that when we transform an integral just in 1D to get it easier, we already have done this for the general 2D or 3D case. That is a substitution. In this sense, the relation between global coordinate x and local coordinate x, then as we know, the integral is transformed in this sense that the limits x1, x2 gets now the limits psi1, psi2. The function f can be expressed by psi and eta. That is also what we have, because we have there the basis functions as a function of psi and eta, and have to take the gradient with respect to psi and eta. And that is the determinant is simply in 1D just a derivative of x with respect to psi. Okay, so now if we go to the 2D case, we already had here this relation when we were doing the mapping of the elements. So we have here exactly this equation here, that the global coordinate x can be expressed by its value at the nodes, and this shape function being a function of psi and eta. Yeah, and what we now have to do is exactly the following, that that we have this function f now as a function of x and y. X is a function of the local coordinates psi eta, y is a function of psi eta. That means when we take now a derivative of this function f, we are looking here, with respect to psi, it's a derivative of f with respect to x, scaled by the derivative of x with respect to psi. Yeah, plus, since it is a function of psi and eta, the derivative of f with respect to y and y with respect to psi. Exactly here, I just want to get it here, our function f. Yeah, and the partial derivative of f with respect to eta is very similar. As you see, we have the derivative of f with respect to x, and now x with respect to eta. And since f is also a function of y, we have the derivative of f with respect to y and the partial derivative of y with respect to eta. And if we look on the right hand side here, we can now write it as follows. In a vector, the partial derivative with respect to psi and eta operating on our function f, and make here this 2 by 2 matrix where we have the partial derivative of x and y with respect to psi and eta, and scaled by the derivative of this function with respect to the global coordinates x and y. Yeah, and that is exactly the Jacobian, what we have just written down formally before, the partial derivative of the global coordinates with respect to the local coordinates. And that is something which we can compute, because we have, because we have, when I take this here, we have here exactly these relations here between the global coordinates x and y with respect to the local coordinates psi and eta. And that means that the global derivatives of any function which were our basis function with respect to x and y can be expressed. Here we have to put the Jacobian on the left hand side. Therefore, we get the inverse of the Jacobian scaled with something what we can compute, because computing the partial derivatives of the basis functions with respect to xi and eta is in this case a simple task, because we know these basis functions as a function of xi and eta. Okay, so that means we have now all our building steps. So the very important thing is that we have our basis function as a function of the local coordinates, and we can do now the following, that we can compute this Jacobi matrix, because it is nothing else as the derivatives of the global coordinates, which can be expressed by the local coordinates with respect to the local coordinates. Yeah, and clearly what we need, as we have seen, is not really the Jacobian matrix, it is the inverse of the Jacobian matrix, and that means it has to be invertible, otherwise we get in problems, and that is just a question of the shape of your global elements. So, and that gets singular if the mapping is not unique. What does this mean? I will go back to here. You will never have a problem of such an element. Yeah? So we look here now at the global space, at the global space. And if you have any element in the global space which is looking like this quadrilateral, then it will be no problem. But we can also have then, starting like here, more deformed elements. So still this element will be okay. Such an element will be not okay. Yeah? So this element will be not okay, and you will get a negative Jacobian. Okay, clearly the best element is also in the global space when you have really these nice elements with 90-degree angle, but for complex domains it will not be able to get a computational mesh with such nice elements. So we should always have a look when we do the meshing of our computational domain, that the angles we have is in a quadrilateral are somehow near 90-degree, and that you can also achieve when you have a mesh. In most grid generators you have the possibility to do a smoothing after you have got the first mesh, and then the algorithm tries to redistribute the finite element nodes in such a case that these strongly deformed elements get a better shape. Okay, so in this sense, the Jacobian defines how differential operators are transformed, as we have seen, and clearly also its determinant gives the change in a line in the surface or volume integral, which we have to evaluate in order to get the entries of our system matrix. Now, clearly for simple functions, we could do the integration by analytically evaluating them. However, in the finite element method, you mainly do, as you can see here, such an approximation that instead of integrating, we have a sum where we evaluate our function at specific positions within this element. Remember, we integrate over the reference element, not over the global, somehow deformed element, over the reference element. And we even can scale each evaluation by a weighting function W. Yeah? And due to this fact, we have some additional freedom we have some additional freedoms how to choose the positions xk in the elements and wk. And the number of integration points will then give us the integration order, and we clearly will look for optimal locations and optimal weights in order to get highly accurate numerical integration. And that is shown here. What we actually will use will be Gauss integration. Gauss integration rules have the weighting function and special positions where we evaluate. And as you can see here for the Gauss quadrature, we even do an exact integration of polynomials which have a degree which is smaller 2 times km minus 1, where km is the integration order. Yeah, which means for us that in most cases for the bilinear quadrilateral that we use 4 integration points, and that is as shown here. We evaluate this by this double sum. We have to go in psi and in eta direction. For each direction we have a own weighting function, and perhaps you are not exact and you make some error. That is why we also have there now this e. This is here, you perhaps make the error. But what you can do, you can combine this double sum to a single sum and evaluate your function at specific locations within your element. And these locations are as follows. You can see it here. You know that psi and eta have the limits minus plus 1, and you see that is somehow at the positions plus minus 1 over the square root of 3, and you see all the weighting functions are exactly 1. So these are the evaluation points at which we evaluate our functions we have within the integral, which is the gradient of the first basis function dot product with the gradient of the second basis function. And at each integration point 1 to 4, we have to evaluate it. In each integration point, we have to compute the Jacobian, we have to compute the inverse of the Jacobian, and we have to compute the determinant. And that clearly shows you that it is some work in order to get the entries of each element matrix, which we then assemble to the global system matrix, which is quite different. If you use a standard finite difference method, you will not have such a lot of computational steps in order to get your system matrix. Yeah, and what are the steps you have to perform? And for this case, I have prepared a computational grid which has just, as you can see here, 2 elements, and it will be according to our Poisson equation we have discussed. So we have here the node 2 and the node 1, and here we have at these nodes directly boundary conditions, and we have element 1 where we have so-called global nodes. Yeah, so we call this the global nodes is 1, 2, 3, 4 up to 6, and we have the local nodes which are always going from 1 to 4 because each element has 4 nodes. And what you do now, as I have told you, we want to have a simple procedure we can implement on the computer so that we know when we have computed an element matrix, which we can now do with this mapping concept, how is the assembly procedure, how we take each of these element matrix entries and where we have to put it to the global system matrix. For this, you first set up a so-called nodal equation array, which means you just go through all your nodes and you put 0 if the unknown is already known there. It's a Dirichlet boundary condition. And in the other case, you just provide a number going from 1 to the number of equations. And then we have it as follows. As you can see this array here for the first global node 1 and the first global node 2, these two, what we have here, we give 0 because we already know the solution. There we have a Dirichlet boundary. And then we go on with node 3, 4, 5, and 6. And the ascending order, we give the equation numbers 1, 2, 3, 4. Okay, so in our case, we know at the end we should have a system matrix just with 4, in this case, unknowns, which we want to compute. And that are the unknowns at this node here, at this node here, at this node here, and at this node here. Okay, so that is a simple procedure you do. You just go over all your finite element nodes, which you have obtained from the mesh generator, and put an equation number there or 0 if it is a node where a Dirichlet boundary condition has been prescribed. The second gives you the relation between the global node numbers and the local node numbers. And for this, we have here the following relation. We have always 4 local node numbers because we have quadrilaterals from 1, 2, 3 to 4, and we have 2 elements, yeah, the element 1 and the element 2. And if we look now to our computational mesh, then we see the following. The local node number 1 has also the global node number 1. Yeah? And that is why we have here, I just change why the entry is here 1. And then we go further. We have here node number 2. Node number 2 has a global node number 3. And that is why we have now here the value 3 and so on. So this gives you the relation between the local node numbers and the global node numbers. And if you have this information, then it's also easy to get for each global node number the equation number, and that is the equation array. You go in with a local node number, A is a local node number, and the element number. We have just elements 1 and 2. And as you can see here, the difference between this information element node array and the equation array is that the entries here are now the equation numbers. Yeah? And as we can see here, node number 1 has got no equation, that's why it is 0. Node number 3 has got the equation number 1. Node number 4 has got the equation number 2, and node number 2 has got the equation number 0. For the second equation, we should have everywhere entry different from 0 because we have no Dirichlet boundary there. Okay, so you see also to set up the equation array in this sense is not a so difficult task. And we can now go and look what happens. As I have told you, since we have subdivided the computations from the global computational domain to each element, for each element, since we have 4 nodes, we will always get a 4 by 4 matrix. If you have a linear triangle, you will have a 3 by 3 matrix. If you have a hexahedron in 3D, you will have 8 times 8 as a size for the element matrix if it is first order hexahedron element. Okay, and what we have here is the following. It is clear that the first 2 nodes they are directly nodes. So all the entries we have there should not contribute to the system matrix. So just those who have here the parentheses, and these are these four. You cannot see it. One moment, I will take my pen. Exactly. So just these four, yeah, they will contribute to the system matrix. The others will not contribute because we have their entries in our equation array, which is 0. For the second element, all the entries you have computed for your element matrix will be assembled to the system matrix. Yeah, and what happens with the right-hand side? Let's say on the whole boundary, you have some values different from 0. Here it is exactly the same, that just these two will also enter your right-hand side vector, and here all entries will enter your right-hand side vector, because for the second element, for each node we have there, we have an equation, and therefore we will assemble. Okay, and that is how it will look like. So you see here always the indices are according we have here, as you see here. These are the local node number 2, 1, local node number 3, 1, for example, and the superscript will give 1 for the first element and 2 for the second element. And you see for the assembling, it is you first set your system matrix to 0, and then you go over this assembling loop, and you always add what is already there in your system matrix. And that is the simple algorithm, and that is as we will have it in all commercial or research programs. So you go over all finite elements. I should get my pen. So this is important. This is this. E is the index of each finite element. For each finite element, you make a loop over all element nodes. Yeah? This is the index A, which goes from 1 to the number of element nodes. For our quadrilateral, it was 4. And then you already evaluate your equation array. The equation array, as you remember, was the local node number as the first index and the element number as the second index. And when you get a value out which is larger than 0, you know, okay, you got an equation number different from 0. You now go and make the loop again over all element nodes with the index b. So it also goes from 1 to the number of element nodes. For us as a quadrilateral 4. And here you do the same evaluation to get the second equation number. Now we have here b, so it is the local node number you have of your element, and e is the element number what we get from the outer loop. Now, if you also get out a value larger than 0, you know, okay, this entry of the local matrix has to be assembled to the global matrix. And the position is clear. It is at the position equation 1, equation 2, exactly what we have obtained here, equation 1, equation 2. And as you see, you just add the according entry of your element matrix to your system matrix, which you perhaps have already entered. It's clear if I go here back and just make our 2-element example. So then it is clear that, for example, this node here, here we have a node, and here we have a node, then it is clear that from the element matrix of this, we will get the entry, and here we will also put the entry, and when we have the element matrix of the first element, then we also will get here and will add something to the equation according to this node and also add here something. Yeah, because they share this common edge between these two elements. Okay, and that is actually the so-called assembly procedure you have to implement. And we have learned the following. We have seen how we can evaluate very efficiently our system matrix entries. We go first from the so-called global side to a local side where we compute this for each finite element we have within our computational domain. Due to the mapping, we can evaluate to get the entries of this element matrix very efficiently. On the other hand, don't forget, you always have to compute the Jacobian of each integration point in the element. You take the inverse of the Jacobian, and you also need the determinant of the Jacobian. But with this procedure, with a numerical integration scheme, you get it at least efficiently for this approach. And then you apply this, what we just have discussed here, in order to put the entries of your element matrix to the correct position in the global system matrix. Yeah, that's all in this sense what you have to apply. Okay, that is the approach when you do the following, as I have told you, that you say, okay, when I already know that at the node I have a Dirichlet boundary condition, I do not apply their equation number, which means, but that also means that we will have some additional contributions to the right-hand side. A second approach could be the following, this general approach, how to handle Dirichlet boundary condition. Well, you could apply to all nodes an equation number, yeah? Which means, in this sense, you get now an algebraic system of equation where we have, as shown here, you get this, but in our solution vector, we will have entries which include more or less our already known values at the Dirichlet boundary. On the other hand, that's not a problem, because we will now reduce this system to a system where we just will have the unknown physical quantities at all the nodes. And that we do as follows. In this sense, we first introduce a so-called column vector bi, with which we compute the unknown, the vector of all the unknowns, also including the Dirichlet boundary conditions, to get out the specific Dirichlet boundary value. And if we collect all these column vectors, we will get a matrix. And the matrix means if we apply the matrix B on the vector U, including the unknowns as well as the known Dirichlet boundary values, we will just get out a vector including the Dirichlet boundary values. And as you can see here, I have written here B, and B in this sense is nothing else. The dimension is the number of Dirichlet boundary nodes times the number of nodes. We had in our case 6 nodes, 2 quadrilateral elements due to the fact that they are glued together, they have 6 nodes, and we had 2 boundary nodes where we already know the Dirichlet boundary condition. Okay, and then it is clear that at this position and this position we have 1, because then all the others have 0, then all the unknowns will be 0, and what will be left will be in this case just the vector with the 2 entries of the Dirichlet boundary. Now, in a next step, what we do is we sorry, we introduce now a vector phi, and when we multiply this matrix B we just have set up with this vector phi, we should get 0, which means phi should include these values ui minus u directly boundary at node I. And when we now go further and we take this away, then we can say we introduce now the reduced vector of unknowns. The reduced vector of unknowns in our case would be from 6. We reduce it to 4 because actually in our case we had 4 unknowns and 2 values at the boundary we already know. So we introduce it via a matrix C that we get here all these entries when we multiply this reduced unknown vector by this matrix C. Going back where we have defined B phi being equal to 0, it will be now BCW. Now, this C matrix also just simply includes 0 and 1. And for our case, it is this simple matrix that we have here starting with row 3 exactly on the diagonal, say entry 1, because these are now those when we multiply this with our vector that we get out these nodes where the physical quantity is unknown. And you now see, since the first block has just zeros, we will reduce by the multiplication of our system matrix with C transposed from the left and C from the right, reduce this to a matrix which is just a 4 by 4 matrix. And this is multiplied by the vector of the really unknowns. And here you reduce your right-hand side, and what you get here is the additional values on the right-hand side due to the directly boundary conditions. Okay, so if you then compute and get here all the entries of this vector W, you can transform back by this simple relation, and then you get the solution vector including the solution of the unknowns and the directly boundaries you already have known from the beginning. So this is a second approach. It perhaps depends how many directly boundary nodes you have. If you do this approach or you do the approach as I have shown you before, where we really introduce equation numbers and we just gave to these nodes an equation which are not a directly boundary node. Or you start it as we have seen here, directly that all nodes get the equation number. You get a system here where the vector u not only include the unknowns, but it also includes the directly value, and you reduce it as we have seen here by this C matrix and project it in this case to a matrix which then just computes the unknown quantities of our physical quantity. Okay, so this was an introduction to the finite element method. Let's give a summary to it. And the summary, as you see, is as follows. The important thing for the finite element method is we do not solve the partial differential equation. We solve the weak form. And we get the weak form when we multiply the partial differential equation by a test function and we integrate over the whole computational domain. In a second step, so this was our first step, in a second step, then we apply the divergence theorem, and that releases the order of the spatial derivative on the unknown quantity, as we have seen. First, it was a second space derivative in this Poisson equation, and after this application of the divergence theorem, we have just a first order spatial derivative, in addition also a first order spatial derivative on the test function. Please also consider this very important thing we have seen, that our material parameter, which has also a spatial derivative in the strong form, now in the weak form has no spatial derivative, which is very important, especially for us in electromagnetics, where you also have jumping material parameters. For example, the interface between air and iron, where you have a strong difference in the permeability. And in this sense, as you can see here, you have no problem because the material parameters enters the weak form without any spatial derivative. Yeah, and then we have seen that we do this element local ansatz, we do the mapping in order to be able to define our basis function in order to be very efficient by performing the integration and by computing the spatial derivatives. This is this case with this reference element, and you have seen that by breaking it down the computational domain and not integrating each entry of the system matrix over the whole computational domain, we break it down to each finite element, and therefore we also have this so-called assembly procedure to be considered, but so we are clearly more efficient because we will have just local connections, and that is also due to this sparsity and the local support of the basis functions. We will have at the end a system matrix which is sparse and have just few entries being different from zero. Okay, so I hope you have obtained the overview about this more mathematical approach, how to solve a partial differential equation with the finite element method. And in this case, it is any partial differential equation you can just take. The procedure is always the same, and you do this weak formulation and do then